Hey, you know, that's not that bad given my spindle speed and the tooling I'm using. That's supposed to be a hammerhead. All right, calm down, calm down. This isn't what you think it is. Okay, it might be what you think it is, but this isn't another wood video. Just our victim. Easy prey, if you will. But you know, you really shouldn't be so raw materialist. It's 2021 for crying out loud. No, you're right. I've been starting in on a lot of videos recently. Not published yet because they're not finished, but it feels like I've been doing metal projects, and I didn't realize we did 2 wood videos back to back. Won't happen again. Pinky swear, probably. But you're not here to listen to my life story, so let's tuck in. Today, I want to show you a little CNC trick. I'd like to talk about a 15-year-old groundbreaking technology and what it can do for you. As usual, I've already mentally prepared a 40-minute introductory TED Talk about the subject, but this time we'll do things a bit different. First, we need a janky surface, and that's where this comes in. If you're not sure what janky means, in machinist terms, it usually means not flat. There we go. My intention was to go jankier, but that should do. Looks a little unnatural, but we've got our janky block in the CNC machine. What we need now is some G-code. For this demo, we'll just engrave some text. Nothing fancy, nothing complicated. I still haven't gotten through my first cup of coffee. Though I'd like to point out one thing in particular. Notice this G-code is planar. It's 2D. It's flat. As is, it would successfully engrave text on a flat surface. Notice the red rapids and the vertical lead-ins, they all stop on a flat surface. No tricks up my sleeve. However, I'm going to cut into this. They don't call me this crazy Tony for... Is that the coolest thing you've never seen or what? I know. Half of you are wondering how on earth I did that. The other half of you probably already mumbled it under your breath as you scroll through the sidebar looking for another video to watch. Surface mapping. Surface mapping, sometimes called mapping the surface, is a technique that sort of maps regular G-code, meaning G-code maybe not already meant for complex surfaces, onto non-flat, possibly janky surfaces. Though this would totally work with 3D G-code too, if you need to fit it to some material variation maybe, but that's hurting my head just thinking about. Some of you might be saying, hey, that's just like G-code wrapping for cylindrical surfaces. No, it's nothing like that. Well, okay, fine, maybe it's a little like that. Let's walk through how you do this. It's surprisingly easy, and then we can talk about where this might be useful. Let's start off with this block. This is the same exact block we just engraved into, but I've jumped back in time to before the engraving. We'll just repeat all the same steps as before, since frankly we have no choice, we're in a time loop now. The first step is to develop the surface map. The surface map is just a list really, a table of information. That information being the z height, the height of the surface, at specific x and y coordinates. So say you start here, the surface has a certain height, measure that height, move a little, measure it again, move a little more, measure it again, etc. and so forth, until we've created a height map of the entire surface. In order to do that accurately, we'll need a probe. I have this fancy one on loan, which is wireless. I've never used a wireless probe before this, and I managed to break it the day I got it. Turns out, I'm the reason I can't have nice things. I installed it in my spindle and it wouldn't come back out. It's not in a tool holder right now, but it was in the spindle. I released the tool clamp, but it wouldn't budge. I stepped away to find a hammer or a pry bar or something, I don't know what I was thinking. The minute I got out of arm's reach, it dropped right out and smacked into the top of the vise. I don't know what happened. I mean, I was walking backwards real slow and everything, even staring at it the whole time. I couldn't have been more cautious. It used to have a nice ruby tip. It doesn't anymore. This is a Drewtronics S5100, I think. You can probably read that better than I can. Like I said, it's wireless and really nice. I might not give this back. In fact, I may have bought it the second it hit the vise. Anyway, I've ordered a new tip. 2 actually. And for now, I've just glued on a small ball from a bearing. I can't really do much with this as is, but it should be fine for surface mapping. Close enough anyway. I really hope the new tip fixes this and I didn't do permanent damage. These things aren't cheap. In fact, wireless probes in general are pretty expensive, no matter the brand. And strictly speaking, I don't even need the wireless version. You'd go wireless if you had a tool changer on your machine. I have no tool changer. A wired one would have done exactly the same job, except there'd be a wire sticking out the side. It'll tell you in the software, but I've done this already. I'm going to start the probe off in one of the corners. I'm doing this in Mach 4 using the wizard. You'll see that in a minute. But it'll need 2 opposite corners to define the area that we want to probe. This wizard works in machine coordinates, so I'm going to start there. And like I said, it's a wizard, so select wizard, MC surface map. These are the positive and negative extents I mentioned, and I'm already at X max and Y max. Now I'll jog the machine to the opposing corner. Click those in so the wizard picks that position up. Basically, you're moving your machine around and just pushing a button to enter the data. I guess you could type it in if you were braver than me. That's the Z start, sort of the clearance plane, somewhere above the highest possible point on our janky surface. The other values are self-explanatory, I think. It's just how tight of a grid you'd like to map, the X and the Y steps. This milling machine happens to be German, so it's metric, but my brain still works in inches, so I'll do a probe distance of 3/8 of an inch, approximately 10 millimeters. That should be enough to catch all the variation. It's telling me it's about to do 108 points, so I'll speed this up for you. Now I just hit the go button, do surface map. When finished, it'll prompt you to save the map. The little report here also tells me the deviation on this part is less than I expected, around 4.5 millimeters. Hit OK. I'll need to disable. Now we can call up or activate that surface map we just generated. Plugins, surface map, add map, navigate and select the map you just saved, apply it, OK. The machine now has a little special height map inside of that area we probed. Anything outside of that is still flat, or whatever your machine used to be before, I guess. Here's that flat G code again, and cross your fingers. Perhaps it's me, I am easily amused, but here's the part that blew the little I have left of my mind. The surface map isn't doing anything to the G code. I mean, I guess it's a matter of perspective, but really isn't everything. The surface map is distorting your machine. It's warping space-time. I'll admit, after running this the first time, I panicked a bit, broke my machine down and measured all the ways. They're still flat. Fortunately, the map didn't warp the cast iron. Check this out. I'll bring up the display. We'll switch out of machine coordinates. I'll zero those DROs. And I'm simply going to jog the machine in X positive. I'm going to use the right arrow key on the keyboard. No G code running. I'm literally just moving to the right, and you watch what happens. Notice that the tool is following the surface, but the Z DRO isn't changing. So despite moving up and down in the real world, Z is still always at 0 because that's the definition of the new 0 surface. There's a little fluctuation here on my machine because the Z-axis is so much slower than the other two axes, but we're talking fractions of a thousandth of an inch. It's just the inertia in my particular machine. Truth be told, I wanted to do this demonstration with an indicator in the spindle. Sure, it's impressive seeing it digitally on the screen, but a needle not moving as it swept across this wavy surface I think would have been a great demonstration. However, in my shenanigans making this video, I took this block out of the vise. I have no stop, so I would have never gotten it into the same position. I don't know if you can make it out, but I got some drag marks when I tried to do this right at Z0. Some of you may have noticed slight fluctuations in that Z height. And that's really why I'm bringing this up now. To do this right, once I took the block out and put it back in, I would have to run another surface map. That, or again, I should have been smarter and set up a stop on one side so I get the block into the same exact spot it was when we mapped it the first time. I can't tell you why I was itching so bad to try this. The results are exactly what I expected. I guess I just needed to see it. I loaded the surface map we generated using this crooked block and used that surface map to cut a pocket into this flat block. This was 2D adaptive pocket clearing in 2 step downs. 11 times out of 10, that would get you a pocket with a flat bottom. But with surface mapping, we basically copied the original surface over from here to here. Hopefully you can see it better in the side view. I'm not sure where this surface lines up. Maybe about there-ish. If you were really intent on copying a surface, you'd probably use a denser map to begin with, and maybe not cut with a big-ish flat-bottomed end mill. But you get the idea. We basically just digitized the surface and used that to machine a copy, just like they did in the 80s. All right, that's it, I think. I apologize for my lack of imagination this morning. I'm sure a more clever person than me could come up with some better demonstrations. Right now, my head is stuck in engrave mode. But not long ago, though you'll have to wait till next week to see it, I wanted to V-carve something onto a complex surface. Like V-carve a 2D design into a 3D surface. Turns out, V-carve doesn't let you do that. Or doesn't let me do that. At least my version of it anyway. This would have solved that problem. Heck, would have made things easier, I think. Imagine, if you will, you wanted to checker the stock on your granddad's shotgun. Don't do it, you'll regret it. But just say you wanted to do that for argument's sake. And you suck at 3D CAD. Even if you didn't, imagine the headache of getting that all set up and lined up straight. I mean, really, what are the odds of you digging up the 3D CAD they used back in the 1890s to make it? But what you could do is draw or download a 2D checkering pattern. Probe the stock, just like we did with the other block, run the flat pattern, and get custom fitted checkering. Okay, granted, that may have been an overly specific example, but hopefully you get the idea. And speaking of 3D engraving, you could use this, I think, to do very, very clean inlays. If you invert the surface map, something I haven't tried yet, but if you invert it, you could cut the negative. Or wait, would it be the positive? You could cut the opposite. Glue the parts together, then take a few skim cuts to reveal the inlay underneath. Hold on, let's walk through that with a graphic. You cut one part, part A, invert the map, use that to cut part B. Those two would then nest together. You glue them, let that dry, and then use the original surface map, I think, to skim the top off, revealing the inlay inside. At any rate, surface mapping is a very specific tool, sure, but one more for the toolbox. Good to have in the old bag of tricks. I hope you like that. If you already use this stuff, or if you come up with any cool ideas for this, I certainly invite you to leave them down in the comments. Until next time, thanks for watching.